Okay, so welcome back to the second video on cross products, volumes and hypervolumes. What I'm trying to do is give some intuition as to why, if I take two vectors, so here, here is the two-dimensional plane, why if I take two vectors, let's say here is A and here is B, why the area of the parallelogram spanned by these two vectors is given by the modulus of A1 B2 minus B1 A2, basically, which we can view as being the modulus of the determinant of the matrix, the vector A1, the components of the vector A are in one column here, and the components of the vector B in the other column here. Why that formula works, basically. Okay, so the reason is that if we imagine dropping down a parallel line, dropping down a line here that is perpendicular to this vector B. So imagine dropping down the line there that's perpendicular to the vector B, so that you get basically here a right-angled triangle. Well, if I were to just shift that right-angled triangle up here, then that would complete that the space left there, and it would make this a nice rectangle. A rectangle of length, of side length here. The side length of this bit here would be the length of the vector B. So this side length here is length of B, so I'll just put L of the vector B to denote length of vector B, because it's got this bit here from B, and then this bit that we added on over here came from this bit of B down here, so its length is still B. All we need to figure out is what is the height of this perpendicular line here. Okay, so we want this height. So what you will notice is that height is the component of the vector A in the direction perpendicular to the vector B, basically. So if we found a vector that was perpendicular to B, so some vector here that was perpendicular to V, and we took the component of A in the direction of B, i.e. we took, well, how do you take the component of a vector in the direction of another vector? So let's call this vector B prime here. How do you find the component of A in B? What you do is you take the dot product of the two. But that will give you, remember the definition of the dot product is it will give you the modulus of A times the modulus of B times cosine of the angle between them. So here is the angle between them here. So the modulus of A times cosine of theta, if we just think of this as being a right angled triangle, so I'll just draw it out here again. So here is our vector A here, so it's got side length modulus of A. Here is our angle theta. We are taking modulus of A cos theta. That's going to give us the length of this side here, mod A cos theta, i.e. it's going to give us the height. It's going to give us exactly this height here. It's going to give us the component of the vector A in the direction perpendicular to this vector B. So here is the vector B. This was, remember, the vector B prime. Unfortunately, of course, this dot product is going to also have this modulus of B prime, that should be, modulus of B prime term. So what we'll need to do is divide through by the modulus of B prime, and that will give us the height of this component here, basically. Excuse me a moment, the computer's doing something. Okay, that's fine. Okay. So this will give us the height of this bit. So all we need to now do is multiply this bit here, where we've divided through by the modulus of B prime, and all we need to do is then multiply it by the modulus of B. Okay, so I'll put the modulus of B there, and that will give us the area of this rectangle, because this was the length of this side here. The modulus of B was the length of this side, so that overall will give us the area of this green rectangle, and we know that the area of the green rectangle is the same as the area of the original parallelogram, so problem done. However, there's something clever we can do here. Instead of saying, oh, sorry, I'll put the modulus of B here just to make it complete. Instead of saying let's divide through by B prime, what if we made the modulus of B prime the same as the modulus of B? what would that do? That would mean that this beautifully cancels with this, and then we'd get the modulus of A dot, the vector A dot producted with this vector B prime, and now we've got a complete specification for this vector B prime, because we know what direction B prime has to be in. It has to be perpendicular to the vector B, and it also, we know its modulus, it has to have modulus equal to the vector B. So basically, this vector B prime is going to be equal to the vector B. You take the basically you just rotate the vector B by 90 degrees, and that's going to give us it's going to give us this vector perpendicular to B with modulus B, and then if we dot product that with A, it will give us the area of this rectangle. Of course, there is this slight risk that you might end up with the opposite vector, i.e. you might end up with the vector pointing this way, because that's also perpendicular with modulus B, in which case you'll get the exact negative answer. So if we take then the modulus, if we take the absolute value of the dot product of A with this new vector B prime, where we have the specification that B prime is perpendicular to B, so I'll just draw perpendicular to B, and we know that the modulus of B prime is equal to the modulus of B. So that gives us two possibilities for the vector B. Right, so how do you take a vector which is, how basically do you go from the vector B to having the vector B prime? Well, the vector B has components B1 and B2. This is its x component, this is its y component. So let's say it's here basically. This is the vector B, and here is its B1 component and its B2 component. Basically, the way that you construct a perpendicular vector to this with the same modulus is you take you swap the two terms round. So you say, okay, let's go in B2. Basically you swap the components, so you make B1 your amount in the y component and B2 your amount in the x component, and one of them you have to make negative. And the reason this is perpendicular to this is because if we take the dot product of those two things, B1, B2, dot product is with negative B2, B1, like that, we're going to get these two multiplied together, which will give us negative B1, B2, and these two multiplied together, which will give us plus B2, B1. I.e., you'll get 0, which is exactly the criterion for being perpendicular. If you've got two vectors which dot product together to give you 0, they are perpendicular. Okay, so I found you a vector which is perpendicular to B, so this negative B2, B1, and note that the negative of this will also be perpendicular to B. So if I took the vector B2, negative B1, that would also be perpendicular to B. It's arbitrary which one you want to choose, and it doesn't matter because, as I say, we're going to take the modulus of this dot product in the end. Let's also check that it satisfies the other condition, that the size of this vector is the same as the size of the original B vector. So the size of the original B vector, the modulus of B, was equal to the square root of, just using Pythagoras' theorem now, the length of this vector here is the square of the lengths of these two sides square rooted. So the B1 is B1 squared plus B2 squared. And if we take the modulus of this one, the modulus of B prime is going to be equal to the square root of negative B2 squared plus B1 squared. So just put both of those components in. And because when you square a negative, it just becomes a positive, this is exactly the same as up here. So we do indeed get that criterion. So basically what we have now is that the area of this parallelogram is going to be the modulus of the vector A dotted with this vector here, which is negative B2, B1, basically. Okay? So now stick in what A is equal to, and we get the modulus of A1, A2, so I'll move this up, dot producted with negative B2, B1, and take the modulus of that. So if we dot product this, we get the negative A1, B2, so we're just multiplying components and adding them together, so plus A2, B1. So, if we go back and compare this to what we originally had, obviously what we've got in here is the exact negative of what we've got in here, but because we're taking the modulus sign, it doesn't matter. That's exactly the same as A1, sorry, you can't see this. This thing here is exactly the same as A1, B2 minus A2, B1, because if I multiply the inside by negative 1, when I take the modulus of that, it will be exactly the same as if I hadn't bothered. So this in here is exactly the same as this. Okay? And this thing here, this A1, B2 minus A2, B1, is equal to the determinant of this matrix that we had, A1, A2, B1, B2, where we put the components of our vectors in these in the columns of this. When we put our vectors in these in the columns and wrote each component in the corresponding row. Okay. So that is the reason that this formula works, basically, up here. That this formula for the area of a parallelogram spanned by two vectors A and B in a plane works. And you can either think of it as going through the steps of the cross product, or you can think of it in terms of this argument in terms of dot products. In my opinion, this argument in terms of dot products is very, very useful, because when we want to go further into, when we want to generalize this to 3 dimensions, we're going to see this argument in terms of dot products again, basically. We're going to see that what we'll do again, when we have, for instance, in 3 dimensions, when we have, where we have 3 vectors, so let's say a parallelogram like that, and then another parallelogram like that, another vector, sorry, like that. So we're trying to take the volume of this parallelogram, of this, well, this 3-dimensional shape, whatever that's called. When we're trying to take the volume of that, what we'll do is we'll find a vector which is perpendicular to this parallelogram here that I've shaded in black, and which has the area of that parallelogram. And then what we'll do is we'll dot product that with this final 3rd vector here, basically, and that will give us the hypervolume. And I'll explain this more in the next video.